Welcome everybody to Algebra 2 1.1, first lesson of the course of Algebra 2. So today we're going to be simplifying radicals, classifying numbers in the number system, as well as simplifying expressions and operations using the order of operations. So our first topic we're going to talk about are square roots. So the square root of a number, a, can be written as a radical expression. So here we have this symbol, and this symbol is called a radical. A lot of times it's considered to be called a square root. We know a name for it. However, we're going to try and call it radicals more often when in general just for that symbol. Well, but we can speak it as square root of blank. This a here, whatever's underneath the radical or the square root symbol there, is called the radicand. The radicand. Now when we're working with radicals or square roots, it's very important we talk about perfect squares. So we're going to list the first 20 perfect squares. So that's a number times itself is that number, or a number squared gets you that number. So try and do these on your own and go and pause the video and work on that. Hopefully you already worked on these. So the first 20 perfect squares are 1. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. 12 squared, 144. 13 squared, 169. 14 squared, 196. 15 squared, 225. 16 squared, 256. 17 squared, 289. 18 squared, 324. 19 squared, 361. And 20 squared is 400. Now, it's not required to memorize all of these. However, it is encouraged actually to try and memorize them. For example, when I was taking Algebra 2 as a course in high school, my teacher gave us quizzes to memorize the first 25 perfect squares. And while I'm not giving you quizzes to memorize these, I do think it's a good idea to work on memorizing them. And I think a lot of them you'll start becoming more familiar with as we work with them more and more. And you're hopefully familiar more with these first 10 already. Now, square root of 25 is 5. Remember, the square root of a number means what times itself is that number. Number 2, square root of 256 is 16. And by the way, on any time we do problems, I encourage you to go ahead and pause the video, work on the problem as much as you can on your own, see what you can do without my help, and then continue the video. 3, negative square root of 121. Well, square root of 121 is 11, so this means it's just negative 11. Number 4, square root of 196 is 14. 5, negative 300, square root of 324, is negative 18. And 6, square root of 9 over 100. Well, square root of 9 is 3, and square root of 100 is 10, and this is 3 over 10. If you did 3 over 10 times 3 over 10, 10, you'd have 3 times 3 on the top, which is 9, and 10 times 10, which is 100 on the bottom. Now we're going to work on simplifying radicals that are not perfect squares. So find the largest perfect square that the radicand is divisible by, and break it down or split it apart using the radical, or using that perfect square is our first step. So let's start there. The square root of 44 on number 7. 44 is not a perfect square. No number times itself is 44. However, it's true that 4 times 11 is 44. So it's also true that the square root of 4 times the square root of 11 is the square root of 44. That is a true statement that you can take these two square roots, multiply them together, and you multiply the insides 4 times 11 and get 44. Now it's also true, you could say instead of this, you could say the square root of 2 times the square root of 22, because it's true that 2 times 22 is 44. So how would you know what to pick? Because you also even could do, in addition to those, is you could do the square root of 1 times the square root of 44, and any of these are factually accurate to say. the two numbers underneath the radical multiply to become the original number of 44. So how would you know which one of these to use? Well, the secret is you want to find the one that has a perfect square. And as we look at these perfect squares that we wrote earlier, the biggest perfect square that goes into 44 is 4. A good way to try to find that if you're not familiar with these problems as well, or especially when you're first starting these, is to start with the biggest perfect square that is still smaller than the number. So 44. Well, 49 is bigger than 44, so 49 could not possibly go into 44. But we want to start here with 36. Which does not go into 44, 25 doesn't, 16 doesn't, 9 doesn't, but 4 does. And doing that helps us get the biggest perfect square. I'll talk about later how if you don't get the perfect square, what you can do in those scenarios. But for now, we're going to start here. So the square root of 44 times the square root of 11. Now, the reason that is helpful to us is because now we can say the square root of 4 is something else. We know the square root of 4 is 2. And so we call it 2 times the square root of 11. The square root of 11 just stays the same. And so what we do is we take the square root of the perfect square, 2. And now it's out of the radical because we already did that operation. Similar to how if you do 2 plus 5, you write 7. You don't write 7 plus blank because you already did the addition. You don't write that symbol any longer. So in the same manner, we already did this square root. We don't continue to write the square root symbol there. And believe it or not, that's actually our answer. It doesn't really seem like much of an answer compared to most problems we have, but it still is our answer. That is the finished version of what we've done. Our goal was to make the number underneath the radical smaller, or the smallest number we could. And that is the smallest number we could, because there are no perfect squares that are factors of 11 other than 1, and that wouldn't make it any smaller, because that would just be saying that it is 2 times the square root of 1 times the square root of 11, which still leaves us with this number being the same size underneath the radical. So we consider that to be answered. Number 8, square root of 288. So once again, we're looking for the biggest perfect square that goes into 288. So if we start with this list, and we say, okay, 289 is bigger, so start to the left of that. 256 does not go into it, and going all the way down the list, we see the first number we find is 144 that goes into it. And 144 goes into, or multiplies / divides into 288 2 times. So it's true that 144 times 2 is 288. So the square root of 144 times the square root of 2 would be the square root of 288. And now we say the square root of 144 is 12. And we leave the square root of 2 as itself. And so we end up getting 12 times the square root of 2. Now, let's say we did not pick the biggest perfect square this time. We just kind of haphazardly went through finding factors of 288 that might be perfect squares. So what we might do is we might have found the square root of 4 times the square root of, well, how many times does 4 go into 288? Let me do some math here. That'd be 72 times. And so what would end up happening here is obviously 72 is quite a lot bigger than 2. But this would be 2 times the square root of 72, and that's obviously a different answer than what we got. So what's going on there? Well, that's because you have to continue simplifying that second radical because it's not done being simplified yet. So we'd say square root of 72, well, 36 is a perfect square that goes into 72. So you'd call it the square root of 36 times the square root of 2, and you continue writing the 2 out in front because we haven't done anything else with it in this step. And now we end up getting 2 times 6, because this 2 stays the same. The square root of 36 is 6, and we leave square root of 2 by itself, or as itself, I should say. And so next we actually multiply 2 times 6, because we can multiply 2 times 6, those regular numbers, those non-square roots together, and get 12. And now we have 12 square root of 2, which is the exact answer we got over here. So if you were wondering, can I choose a smaller number? Does it matter if I choose the biggest perfect square? In reality, no, as far as it affecting your ability to get the answer. We still got the right answer. However, this is a lot more work and steps than this is. So if you can find the biggest perfect square first, that is to your advantage to do. I also want to take note that I draw my radicals different than a lot of people do. So for example, a lot of people don't have this little tail at the end, where I have this little tail at the end of my radicals. That is just a stylistic preference, or just something I like to do for my writing style. It's something I saw my teachers do when I was in math classes, and I started doing it myself. And the reason I like doing it is because I know when this radical ends, so that way I don't think anything else may or may not be a part of the radical, and so I can clearly see when something is or is not part of a radical. But once again, that is completely up to you, whether you want to do that tail like me, or whether you want to be like most people and leave it off. Number 9, the square root of 147. So once again, I'd encourage you to try and find the biggest perfect square that goes into 147. And I would encourage you to doing that with all these problems by pausing the video, working on it, and then playing the video once you've attempted it. So here it would be the square root of 49. 49 goes into 147 3 times. Now, you technically do not have to put the perfect square first. However, I do put the perfect square first. So I put 4, 49, 144 first, and I'll always put that perfect square first, because that way, when I turn that into a regular number by doing the square root like I did here and here, I have that regular number first, because we do want the regular number written before the square root. So here, the square root of 49 is 7. 7 times 7 is 49, and we leave the square root of 3 as itself. Number 10, same kind of problem, however, there's just a negative in front of it. All that's going to happen is our answer is going to be negative at the end. That's the only difference between this problem and the previous problems as far as that's concerned. Now the square root of the negative square root of 80 should be square root of 16 times square root of 5. 16 is the biggest perfect square that goes into 80. So square root of 16 is 4, square root of 5 is just the square root of 5. It doesn't break down any smaller, because the only factors of 5 are 5 and 1. And 1's a perfect square, but it does not make 5 any smaller. And because we had this negative earlier, we have the negative again now. So we get negative 4 times the square root of 5. Number 11, square root of 600. This would be the square root of 100 times the square root of 6. The square root of 100 is 10, the square root of 6 is square root of 6, and we have our answer. Number 12, square root of 162. The biggest perfect square that goes into 162 is 81. And 81 goes into 162 2 times. So because 81 times 2 is 162, we can break down or split up the square root in that way. The square root of 81 is 9, and the square root of 2 is just square root of 2. So now we have 9 square root of 2 as our answer. Number 13, negative square root of 75. So we have negative square root of biggest perfect square that goes into 75 is 25, and it goes into 75 3 times. So the square root of 25 is 5, square root of 3 stays square root of 3, and this negative just stays negative. And we get negative 5 times the square root of 3. Number 14, the square root of 448. The biggest perfect square that goes into 448 is 64, and it goes into 448 7 times. So square root of 64 is 8, square root of 7 stays square root of 7, and that is our answer. Moving on to the next page, we're going to talk about the number system now. So the number system, up to this point in math, we've only used what are called real numbers. We haven't yet used what are called non-real or imaginary numbers. That'll come later in Algebra 2. So the real numbers, or this capital R that's used to abbreviate it, R coming from the first letter of the word, The real numbers consist of the following sets of numbers. So two main sets of numbers that make it up are the irrational numbers and rational. Either something is rational or it's not. So irrational numbers are numbers in which the decimal never ends or repeats. And common examples are pi and non-perfect square roots. Rational numbers, however, are decimals that end or repeat. So rational numbers can always be written as a fraction, something divided by something else, where those numbers are integers. And so smaller groups of rational numbers from biggest to smallest are integers, whole numbers, and natural numbers. Now integers are positive and negatives, however they are non-decimals, and they are non-fractions. So you have everything lower than -3, everything higher than 3, but in between, notice, -3 and 3, you only have non-decimals, non-fractions there. Whereas whole numbers are the non-negative integers. They are non-negative integers. So it's like we just axed out those, and boom, we have whole numbers now. Natural numbers are just the positive integers, or you can think of them as the counting numbers, the numbers we see in nature. When you start counting, you don't start with 0, you don't start with negatives, you normally just start with 1, and you go up by whole numbers at that point on. Now this is a little box here that showcases how these number systems work within each other. So this whole box here shows us the real number system, or capital R. The smaller boxes go in, or the smaller circles go into all of these. And in order to do this well, we can't really write the words like natural on this, or integers, or anything in those very well, or much in there very well. So we need letter abbreviations for each of these. So the letter abbreviation for irrational is the capital I, coming from the first letter of the word irrational. Now for rational, we can't use R since we're already using it for real numbers. And so we end up using Q, and that comes from some language translation from as things got translated into English for different math things. Integers, also we can't use I since we've used I for irrational, so we're going to use capital, my screen just changed for some reason, but for integers we're going to use capital Z, as in zebra. For whole numbers, we're going to use capital W, and for natural numbers, we use capital N. Good idea to take note of those. So here, off in this group are the irrational numbers, or this group are the rational numbers. Now, the first subset smaller than rational are integers, smaller than integers are whole numbers, and smaller than whole numbers are natural. Now I think this graphic really showcases it well, that once you're inside of this, it's still a part of the big circle and this big square, meaning numbers that are natural are also whole numbers, integers, rational numbers, and real numbers. They're all of the groups that they're inside of, whereas integers are not automatically natural numbers or whole numbers. There are integers that are whole numbers and natural numbers, but they're not automatically such as how all squares are rectangles, but not all rectangles are squares, or all freshmen at Plattsmouth High School students in our building, but not all students in our building are freshmen. There's also sophomores, juniors, and seniors. And here we also talked about these letters. Here's another place to organize it if you didn't organize it up above as well. Irrational numbers is the capital letter I. Rational numbers is the capital letter Q. Integers is the capital letter Z. Whole numbers is W. And natural numbers is N. Now notice these are all capital letters. We don't use lowercase letters for these. And that's because lowercase letters are reserved for variables. Now some examples of these different types of numbers to clarify the things I was saying earlier as far as the counting numbers, non-negative integers, decimals that end or repeat, decimals that don't end or repeat, all these different things and others. Irrational numbers we said were like pi or non-perfect square roots, such as the square root of 2 or the square root of 72, Or also this pattern is 1.010010001 going on forever and ever. Very obviously just continually adding a 0, so it's very predictable, but however it never actually repeats by just saying it's 010101 or like 111 or something of the sort. Rational numbers, once again, are these decimals or fractions that end or repeat. So the fraction, or excuse me, the decimal 0.34, or the decimal 1 5/8, or sorry, I should say the fraction 1 5/8, or the repeating decimal 0.2 repeating, where it says 0.222 forever. The fraction -7/11, whether it's a negative or not, doesn't matter. However, you also can include numbers such as 5. 5 ends, it's technically 5.0. And so that ends, so thus it's a rational number. You can also like the square root of 16, because the square root of 16 is secretly just 4. So you could erase that and say 4, and 4 is rational. So thus the square root of 16 is rational, but it just looks weird. Integers. Integers, once again, are negative and positives, but no decimals, no fractions at all. So the number 7 would work. -8 would work. You could say the negative square root of 100, because remember, square root of 100 is 10, so that's really -10. You could do 0. You could do 8/4, because even though it looks like a fraction, 8/4 is secretly just 2, and 2 is an integer. So 8/4 is an integer. Next, for whole numbers, once again, those are the non-negative integers, so 0. You could do 20/4, which is secretly just 5. You could do the square root of 9, which is secretly 3, or you could just 90. Not secretly anything else, it's just 90. And last but not least, for these groups, we have natural numbers. Natural numbers, once again, are those counting numbers, just the positive integers. So no longer including 0 from the previous group of whole numbers. So 10 could be an example. 47 is another example. Square root of 4, which is just 2. Or 34/2, which is just 17. So let's work on classifying these, and we're going to name all sets to which the value belongs. So for example, -10. -10, the small set it belongs in is an integer, so we'll put z for integer. However, because it's an integer, it's automatically rational, q, and it's automatically real, r. So we're going to put z, q, and r. So on some of these, especially if it's a natural number, you're going to be writing quite a lot of letters here, which is why writing letters is very helpful rather than writing the entire word out. I would encourage you to go ahead and pause the video here and practice these examples on your own to the best of your ability, and then come back to the video and keep playing it once you've had a chance to answer some of these. So number 16, square root of 30, that is an imperfect square, meaning it's a decimal that it will never end or repeat. So that will be irrational, and even though it's irrational, it's still part of the real number system, as we can see in this graphic over here. Next, number 17, we have a fraction, 7/9, 1 and 7/9. 7/9 does not reduce at all to a non-fraction, and so that means it is rational, but not any smaller groups. And because it's rational, it's still real numbers. Spoiler alert, every number we'll work with today will also be real numbers, so you should be writing R in each of these boxes. 18, 24/8, it's a fraction, so we might think, hey, rational. However, that reduces to 3. So not only is it rational, but more specifically, it's natural, whole, an integer, and rational, as well as real. 2.48. That is a decimal that ends, so it's rational and real. Negative square root of 81. Well, the square root of 81 is 9, so it's -9, meaning it's an integer. Since it's an integer, it's also rational and real. 21, pi minus pi. Well, even though pi is irrational, anything minus itself is 0. And 0 is whole. That's an integer, it's rational, and it's real. 22, fraction, so we think instantly it's rational. That may or may not be the case, so let's try it out. Take a closer look. Square root of 16 is 4. Square root of 5 is 5. And if we do 4 over 5 times 4 over 5, we end up getting 16 over 25, which is what we see here inside the radical, or the square root. And so we end up having the square root of 16 over 25 is 4 over 5. And yes, 4 over 5 is still a fraction, and it doesn't reduce smaller than that. So it is rational as well as real. Rewriting my R there to make it a little more legible. Number 23, 0.15 repeating. So it does repeat, meaning it is rational. Now, if it didn't end nor repeat, then it would be irrational. But repeating, even though it never ends, repeating numbers are rational, and it still is real as well. 109. While it's a big number to count with, it is still a counting number. It's a non-negative, non-decimal, non-fraction. It's positive. So it's natural, whole, integer, rational, and real. Negative 8 over 3. Though we can make it a mixed number, such as negative 2 2/3, it is still a fraction regardless, meaning it is rational and also real. Square root of 7 over square root of 7 is a fraction, and square root of 7 is an imperfect square. However, any non-zero number divided by itself, such as square root of 7 divided by square root of 7, is 1. So this is natural, because 1 is natural, whole, integer, rational, and real. Moving on. We have the order of operations. Now, this is odd. We see a G here. Typically, we see a P there for PEMDAS, or PEMDAS. Now, even though we normally see P, it doesn't make G wrong. P typically stands for parentheses. G is just talking about more things that go in that same spot, and because it's really any grouping symbol. It's really any grouping symbols. Now, parentheses are our most common grouping symbol, but there's also brackets, braces, fraction bars, and one that's not listed here, absolute value, those straight lines that we sometimes confuse as 1s or 11 or L's. So any grouping symbol belongs in that first step. We first work what's inside those. But if you want to scratch that and call it a P, that is perfectly fine as well. Leave it a G, that's cool too. Next come E, exponents, and any roots such as square roots that we're most used to now. We will have other roots later, but don't worry about that for the moment. M and D are in the same step because you don't do multiplication and then division. You do multiplication division depending on the order you see them from left to right. So if the division is on the left and multiplication is right, you do the division first. Same with addition, subtraction. Those are in order from left to right, not necessarily just doing all the addition before doing all the subtraction. So there's 4 steps to the order of operations there. And we're going to use these to complete these different problems by simplifying the expression. So we're not solving equations, we're not going to get this equals this, but by the end of this problem, you should get one succinct number, whether that's a fraction, an integer, a whole number, you name it. So once again, I encourage you to work on these to the best of your ability on your own, and I encourage you not to just spam a calculator by typing them all in. Also, you'd have to be careful when you type these in a calculator, because sometimes you might type them in incorrectly without realizing it, because you might have to add extra sets of parentheses. Now you could still type individual portions, like maybe you don't know 2 cubed and so you want to type that into your calculator, you could, but I encourage you not to type this whole phrase or expression into your calculator right away. That would defeat the purpose of you attempting this, and that will make the class much harder later. If you put in some work now to get better at simplifying these by hand, it's going to make you a lot more successful in the long run throughout this course of Algebra 2. So number 1, grouping symbols, this parentheses, we have 11 minus 2 cubed. So inside the grouping symbol, 2 cubed comes first. So that is 8. So we have 11 minus 8 inside the parentheses. 29 minus stays the same. Plus, outside the grouping symbol, we have exponents. We can go ahead and take care of that since it's outside the grouping symbol. 36 divided by 4. So 11 minus 8 inside the grouping parentheses is 3. So you get 29 minus 3. Plus, and because this is separated by a plus sign, which comes later in the order of operations than division. We can go ahead and do the division now if we'd like. 36 divided by 4 is 9. You could also wait to do the division until this next step if you wanted. So now from left to right, we have subtraction on the left, addition on the right. That subtraction symbol might be hard to see. 29 minus 3 is 26. And so now we have 26 plus 9, which is 35. Number 2, 4 cubed minus the absolute value of -8 times 6 divided by 16. So the very first thing would be this grouping symbol, the absolute value of -8. Absolute value is defined as the distance from 0. Otherwise, we can think of it as it makes everything positive. So it's either positive already, and so it stays that way, or it is negative to start and it becomes positive. So the absolute value of -8 is 8. So we have minus that times 6 divided by 16. Now, because exponents come before the step of subtraction, we can go ahead and do this exponent here. 4 cubed is 4 times 4 times 4, which is 64. So next, we have multiplication on the left, so we do that one first before the division. 64 minus 8 times 6 is 48, divided by 16. So next would come this division of 48 divided by 16, which is 3. And so we have 64 minus 3, which gives us 61. Next up on number 3, we have a fraction. So we'll do everything on the top of the fraction separately from everything on the bottom of the fraction. And once those two are done, top and bottom, we'll go ahead and simplify as much as we can between the two. So on the top, we start with grouping symbols, and we have 2 sets of grouping symbols. And so we go in the innermost one first and work our way out. So 10 minus 12 would take priority here. So 7 minus the absolute value of -2 would be 10 minus 12 plus 5 squared, which we can go ahead and do 5 squared to get 25. And the reason we're able to do that now is because it's separated by a plus sign from our other terms. On the bottom, 9 minus 2 squared, we do the 2 squared first, so 9 minus 4. Bringing this over here using an arrow so people can follow my work. 7 minus, in the parentheses, the absolute value of -2 is +2. 2 plus 25. On the bottom here, 9 minus 4 is 5. Next, on the top, 7 minus, in the parentheses, is 27 over 5. On the top, 7 minus 27 is -20, and -20 over 5 now would be -4. Number 4. Once again, do the top of the fraction and the bottom fraction separately to start, and top of the fraction, we look at this grouping symbol. And inside the grouping symbol, we have a power or exponent. So we have 2 minus 9, in parentheses, 2 to the second power, plus the square root of 81. So roots fall in the same line as power for order of operations. And because it's separated by this plus sign from other terms, other operations, we can go ahead and do the square root of 81, which is 9. 9 times 9 is 81. On the bottom of the fraction, the subtraction will come later, but 6 divided by 3 can come now, and we get 2. Once again, using an arrow so my work can be followed easily. 2 minus 9 is -7. So we have -7 squared plus 9. On the bottom, 10 minus 2 is 8. So -7 squared is -7 times -7. A negative times a negative is a positive, so we get 49 plus 9 over 8. 49 plus 9 is 58. Now, 8 does not go into 58 perfectly. However, it does reduce. They have a 2 in common. 2 goes into 58 29 times, and 2 goes into 8 4 times. And that's as far as it reduces. Nothing else goes into both 29 and 4 other than 1. So that is our answer. 15. So once again, we have multiple sets of grouping symbols. We have brackets, parentheses, and absolute value. So we go inside out. So we'll start with the absolute value here. So bracket 15 minus parentheses, absolute value of negative 6 plus 2 is negative 4, plus the square root of 9, root separated by addition, we can go ahead and do that, call it 3. Square outside all of that, over 3 minus 3 to the third. 3 to the third is 27. Using an arrow so my work can be followed, I have 15 minus parentheses, the absolute value of negative 4 is positive 4, plus 3, all of the brackets squared. On the bottom, 3 minus 27 is negative 24. Next up, 15 minus is still just hanging out waiting his turn. 4 plus 3 comes next, and that gets us 7. If you want to put that in parentheses, that's fine. It won't affect anything one way or the other. 15 minus 7 is now 8. So we have 8 squared, which now, since it's positive, you could put it in the brackets or leave it out. If it was negative, you'd have to keep it in the brackets, telling us that we are squaring negative 8, aka negative 8 times itself, rather than it being positive 8 times itself. Or, 8 times 8 and then making it negative, I should say, over negative 24. So 8 squared is 64. So now we simplify 64 over negative 24. And whether the negative is on the top, bottom, or outside the fraction doesn't matter. As a fraction, the number is negative. So even though we see a fraction as two numbers, it's really one number, and it's the entire fraction is a number made up of two individual numbers. So 64 and negative 24 both have 8 in common. 8 goes into 64 8 times, and it goes into 24 3 times, and once again, there's a negative somewhere on this fraction. Whether the negative is on the top, the bottom, or out in front doesn't matter, but there is one negative somewhere on this fraction. Number 6, we have two separate grouping symbols that are not that's not one inside of another, so we can do them at the same time separately. Doing so gets us negative 6 squared times 7 minus 4 over square root of 49 is 7 plus 5 minus, minus, so you can actually see it. Absolute value of negative 5 is just positive 5. Arrow, so you can see my work. Negative 6 squared is 36 times 7 minus 4 is 3. Now, I actually don't really need those parentheses there, so I could erase them at this point. I already have them, so I'm not going to bother to take the time to erase them. And the reason I could know that I don't need that is because if I erase them, 36 times 3 is the same as whether or not I have that parentheses there or not. There's no other operation inside the parentheses. Oops, I thought I had to turn to pen. I did not. 7 plus 5 is 12. And once we finish this fraction, we'll be able to subtract 5. So 36 times 3 is what comes next. And 36 times 3 would be 108 over 12 minus 5. And 12 actually goes into 108 an even number of times. It goes into it 9 times. So end up with 9 over 5. Or just 9 minus 5, rather. And 9 minus 5 is just the number 4. Next up, we're going to work on evaluating expressions when they start out as variables. And so it says, evaluate the expressions given the variable replacements. So we're told this expression with variables and numbers, and then we're told A equals 3, B equals negative 4, and C equals 8. So we just have an extra step based on what we did before, and it's just substituting in these numbers for the variables. Now, when we substitute them in, I always encourage them to be substituted in using parentheses. There's a few times where it's actually required to do. That's mostly with negatives and multiplication, but I always encourage to substitute in with parentheses, and then once you've done that, in subsequent steps or following steps after that, you can remove the parentheses if they're no longer needed. So my first step here is, instead of saying it's a times b squared, it's 3 instead of a. Instead of b squared, it's negative 4 being squared. That's an instance where we would need that negative 4 to be in parentheses, and I'll explain that in a moment. On the bottom, it's 8 plus 12 rather than c plus 12. So on the top, this exponent would come first. Now let me quick note this difference here. There's a difference between negative 4 in parentheses squared and negative 4 being squared without parentheses. The first one tells us we're doing negative 4 times negative 4, which would result in 16. The second one actually just tells us we're doing 4 times 4 and making the result negative. You could think of it as if there's a parentheses around 4 squared and not including the negative. And so that would result in a negative 16. So whether or not that negative 4 is in parentheses there really does matter. And for instance, if you type it in your calculator, either of these ways in the orange, you would get the results you see underneath. So there is quite the big difference between those two. So now talking about that difference, we're going to go ahead and apply it here. So the 3 is going to stay the same, but negative 4 being squared is 16. On the bottom, 8 plus 12 is 20. So you could either put the 3 in parentheses or use the dot or both, either one, or any of those really. And here the 8 didn't end up needing to be in parentheses, but better safe than sorry. Now on the top, 3 times 16 is 48, so you end up getting 48 over 20. 48 over 20. 20 doesn't go into 48 perfectly, however, both 48 and 20 can be divided by 4 and become 12 over 5. Number 8, replacing m and n with the appropriate numbers is our first step. So we have the absolute value of 10 times 2 minus 8 times negative 3 being squared. So 10 times 2 is 20, and negative 8 times negative 3 being squared would be negative 3 times negative 3, or 9. So the absolute value of 20 minus 72. Well, 20 minus 72 is negative 52, and the absolute value of negative 52 would be positive 52. Now on to our very last page of notes for this section. Woohoo, we're getting near the end. We have a lot more of these problems, which once again, if you haven't already been, I would encourage you to pause the video to work on them and then resume the video. So number 9 here, substituting in x is 5 and y is negative 9 yields this. So a couple things to note here is that this negative is outside the 5 being squared. So we'll square the 5 and then make it negative. And the other note is that we have 2 sets of parentheses here, so we'll just have to be careful and follow it inside out. So this gives us negative 25 as we talked about, plus 7 times. Negative 9 plus 2 is negative 7, minus 1. Continuing on, knowing that this means multiplication, so that would come before addition or subtraction. And 7 times negative 7 is negative 49. Now from left to right, negative 25 plus a negative 49 is negative 74. Minus 1 more gives us negative 75. Now I want to note, order of operations says you have to add or subtract from left to right. Remember though, we have the commutative property of addition, not subtraction, but addition, meaning you can add in any order you want. Now, how would that come into play? On this problem, we had subtraction here, not addition. I should change colors to emphasize this. Well, you could change this to adding a negative 1. The 1's still getting minus or negative or subtracted. And you can do these in any order. And so if you did that, you could do an alternate reality or a different set of problem or a different way to do the problem where you get negative 25 and you combine these two first because you can add in any order. So if you add negative 45, 49 and negative 1, you end up getting negative 50. And negative 25 minus negative 50 is still negative 75. So that might be easier for you to do because adding 49 and 1 gets us to 50. rather than doing 25 and 49 gives us 74. It can be a little bit harder to work with mentally or in our head. So that's just a little trick you can use, that as long as you keep the sign with the number, in this case keeping the negative with the 1, keeping the negative with the 49, you can be successful by rearranging that because you can add in any order. Moving on to number 10. Number 10 here, we replace r with 5 and s with 2/3. Oh boy, we are getting into fractions here. 3 times 5 minus 4 times 2/3. Well, a lot of people have some struggles when it comes to fractions, so this can be a great opportunity to work on it and improve. We never get better at anything if we don't try first. So this is a great opportunity to get a little bit better today. 3 times 5 is 15 minus 4 times 2/3. It can be helpful to make the 4 a fraction by making it over 1, anything secretly divided by 1, if you don't see a number underneath it. Now, we can't cross-reduce where we reduce diagonally here, because nothing reduces into 4 and 3, and nothing reduces into 2 and 1. So we just multiply straight across and do 4 times 2 is 8, and 1 times 3 is 3. Now, in order to add and subtract fractions, you have to have common denominators. So 15 is secretly also over 1. Now, the denominators here are 1 and 3. Those are not common or the same. Our common denominator here will be 3, though. So we'd say, okay, we have to multiply 1 times a number to make it 3. 1 times 3 is 3. And because we multiply the bottom times 3, we have to multiply the top by the same number. Because what happens is you're secretly multiplying by 3 over 3. And we said earlier, any non-zero number divided by itself is 1. So you're secretly multiplying 15 over 1 times 1, but you're just making it look different, and you're multiplying it by 3 over 3 instead. So this ends up becoming 45 over 3 minus 8 over 3. 45 over 3 being equivalent to 15 over 1. And now if we subtract across on the top, 45 minus 8, we end up getting 37. The bottom stays the same, over 3. We only change the denominator or bottom of the fraction when we multiply and divide. We do not change the denominator when we add or subtract. Number 11, negative 6 being squared minus 8 being squared, the absolute value of all of that, minus negative 6 times 8. Negative 6 being squared is 36. 8 being squared is 64. These negatives being in a row there, take note of that. Minus a negative 48, which I'm going to go ahead and just call adding there to make my life a little bit easier. 36 minus 64 is negative 28. The absolute value of that plus 48. Reminder, when you have two negatives in a row with nothing between them, you're really adding. The absolute value of negative 28 is positive 28. So you have 28 plus 48, which results in 76. Number 12, 2/5 times a plus 2b quantity squared. We replace a and b with the numbers assigned. So we have 2 over fifths. Ignore that notification. 3 instead of a, and 2 times negative 4 quantity squared. So we have 2/5 times the quantity of 3 plus negative 8 quantity squared. 3 plus negative 8 is negative 5. So we square that before we multiply by 2/5. That would result in 2 over 5 times positive 25, because the negative times the negative. Now looking here, 25 is over 1, and we look to cross reduce. 5 and 25 are both divisible by 5. 5 divided by 5 is 1, 25 divided by 5 is 5. So now if we multiply straight across, 2 times 5 is 10 on the top, and 1 times 1 is 1. So I could put it over 1, or I can just call it 10. Number 13, w cubed minus 4v over the square root of w times v. So we have 2 cubed minus 4 times 18 over 2 times 18, the square root, I should say, of 2 times 18. 2 cubed is 8. 4 times 18 is 72. On the bottom, it would be the square root of 36 by multiplying 2 times 18 together. On the top, 8 minus 72 is negative 64. On the bottom, the square root of 36 is 6. Now, negative 64 divided by 6. 6 does not go into 64 perfectly. However, 2 goes into both the top and the bottom, the numerator and denominator, and we get negative 32 over 3. And as we mentioned earlier, whether this negative is on the top, the bottom, or just out in front doesn't matter as long as there's a negative somewhere on this fraction. Number 14, 2m squared plus 9m, replacing m with 1/4. So 2 times 1/4 being squared plus 9 times 1/4. So 1/4 times 1/4, you can think of it as squaring the top and the bottom individually. So 1 times 1 is 1, 4 times 4 is 16. 9 over 1, you cannot cross reduce 9 to 4, nothing reduces both, and so we end up getting 9 over 4 by multiplying straight across. 2 and 16 cross reduce, however, when you do 2 times 1/16, and 2 goes into 2 once, and 2 goes into 16 8 times. So this results in 1 over 8 as you multiply straight across. So we have 1 over 8 times 9 over 4. As we discussed earlier with number 10, in order to add or subtract fractions, we have to have common denominators. Here our common denominator between 8 and 4 will be 8. And so we multiply this one by 2 on both the top and the bottom. And we get 1 over 8 plus 18 over 8. So that results in 19 over 8. And that's our answer on number 14. So I know fractions aren't very fun, and a lot of us really don't like dealing with them. But hopefully you feel at least a little bit better in your ability to work with fractions after those problems. And if not, I'm sure you improved a little bit anyway. And hopefully you start seeing the results of that going forward at some point. Our last problem set for the day, 15 through 20. Simplify each expression by distributing and or combining like terms. So a quick reminder, like terms are any terms that have the same variables to the same powers. So whether that's no variables or the same variable x's or the same multiple variables like x, y, z, like they have all three for example, or it's like x squared y, whatever it is, the only thing that can be different between like terms are the numbers that you see or the signs that you see. And we define terms as being separated by plus or minus signs. So for example, here are 4 different terms on number 15. So as we look at like terms, we see 16x and negative 7x. They both have x's. And when we combine like terms, we add and subtract the coefficients or numbers with the variables. So 16 and a minus 7 gives us 9x. We leave the variables and exponents alone when we combine like terms, add or subtract. And negative 11 and a positive 10, taking the sign with the 11, gives us negative 1. So this is 9x minus 1. Once again, I encourage you to pause the video now, work on subsequent problems or the next set of problems, and then continue the video after you've had a chance to attempt them. Number 16, our first step here would be to distribute. So we have 13 plus 2 times 3n is 6n, and 2 times negative 7 is negative 14, plus 19n. Combining these n's, 6 plus 19 gives us 25n. Combining the regular numbers, 13 minus 14 is negative 1. And we do want to try to write the ones with the variables before the ones without variables, just so you are aware. So 25n we would want to write first, and the negative 1 we'd want to write second. If you were to write it the other way around, you would have to be careful that you take your negative with the 1 and you make the 25n with a plus sign before it because it is positive. You don't see a symbol before it. However, like I mentioned, we do though want to put the one with the variable first. I will not be counting it wrong if you do it the other way, as long as your negatives and positives are correct. Number 17, be careful here with this negative. But first, we distribute the 6. 6 times c is 6c. 6 times negative 2 is negative 12. Now with this negative, we have to be careful, like I said, because we're subtracting this entire thing. And what can often happen is we think of this as minus 8c plus 1. And so we'd start combining things and we do like 6t minus 8c and we call it negative 2c. And we do negative 12 plus 1 and call it negative 11. But that's incorrect on that second part. So what can be helpful with this is if we change this to a plus sign, and then we have to make every sign in the parentheses following it, so this parentheses, the opposites. So any positives would become negatives, and any negatives would become positives. So this 8c becomes negative, and this 1 become negative, because those are the opposite of what they currently are. So we have negative 8c, or plus a negative 8c, or minus 8c. Either one's the same thing in this case, once they're out of the parentheses, minus 1. And you can take it out of the parentheses now that you're adding it, or now that we distributed the sign to each of these. Now as we combine like terms, 6c minus 8c is negative 2c like we talked about earlier. However, we have negative 12 minus 1. Earlier we might have thought of it as a plus 1 in this scenario. And so we end up getting negative 13. Just be careful there with those negatives outside parentheses like that. We see another problem like that on 19 as well as 20. On 18, combining the y's, negative 15y plus 1y, this is secretly a 1y. You don't see that, and so that's negative 14y. Combining the z's, you get positive 2z, negative 7 plus 9. Next up, on number 19, we distribute the 3, so 3 times 3a is 9a, 3 times negative 5b is negative 15b. I'm going to show you this minus sign again, changing the signs inside of the opposites. So this positive a becomes negative a, and negative 7b becomes positive 7b. So you have plus a minus 7b, or c, minus or negative a plus 7b. So combining like terms, 9a minus a is 8a, negative 15b and a positive 7b gives us negative 8b. On number 20, our last problem of this section, negative 8 times 2x is negative 16x, negative 8 times y is negative 8y. Here, once again with this minus in front of this parenthesis here, even though there's a 3 there, if we distribute the 3, once again we might lose track as we go through this and call it, sure, a positive 15x, because we think if this is a negative 3 times negative 5x. But on this next one, we might lose track of that and call it a negative 6y, which would be incorrect. What we have to do, or what might be helpful to us, is make this plus a negative 3. That way we make sure we note that it's a negative 3 times negative 2y, and ending up with positive 6y. Gotta be careful there. So here as we combine like terms, negative 16x plus 15x is negative 1x, or just negative x. Remember that 1 is implied there if you don't write it. Feel free to write it though as well if you like. And negative 8y plus 6y would give us negative 2y. And that